So far, all we've done is put one branch on a benzene ring. And in that case, you always start with the same reagent, benzene, and you just add different other reagents depending on what electrophile you want to put on the benzene ring. And the benzene will act as a nucleophile to attack that electrophile. But what if you want to put more than one branch on the benzene ring? In that case, the branch that's already there is going to influence how the benzene reacts. And the first way it could affect the reaction is the branch that's already there could push electrons into the ring. Now remember, the benzene is acting as a nucleophile, so if you push electrons into the ring, you're making it more nucleophilic. The more electrons there are somewhere, the more that negative charge on those electrons is going to be attracted to the positive charge on an electrophile. So whatever a branch is, if the branch pushes electrons into the ring, it's going to make that a better nucleophile, and that ring is going to react faster. And so you can say that the ring is activated. And the branch that is activating that ring is an activating group, or an activator. On the other hand, you can imagine the branch on the ring not pushing electrons into the ring, not dumping more electrons into the ring, but pulling electrons out of the ring. And this is acting as a nucleophile because it has extra electrons here in these pi bonds. If you pull those electrons out of the ring, it's an even worse nucleophile. And so the ring will react more slowly, and the ring is described as being deactivated. So these branches that pull, whatever they are, if they pull electrons out of the ring, they're deactivating. And the branch itself would be called a deactivator. So if we just have regular benzene, we add something onto it, it's always the same starting material. But if we have branches on the benzene, we have to worry about whether those branches are going to be pushing electrons into the ring and making the ring more nucleophilic, and so activating it, making the reaction happen faster, or pulling electrons out of the ring, making the ring less nucleophilic and deactivating it. So how do you know if something is an activator or deactivator? The goal here is any benzene with any branches on it at all, you'll want to know whether that's going to react faster or slower than normal benzene. So how can you just look at a branch and tell whether it's dumping electrons in or pulling electrons out? Well, there are a few ways that you can have electrons dumped into the ring. So let's go from the types of branches that push the most electrons into the ring, and then fewer, and then fewer. So the types of branches that push the most electrons into the ring are called strong activators. And you'll recognize a strong activator because you'll have a lone pair on the benzylic position. Remember, the benzylic position is the position that's one atom away from the benzene ring. So here, this oxygen, for example, is on the benzylic position, and you have a lone pair there. So that's the first sign that you have a strong activator. But to have a strong activator, you need one other thing. These lone pairs can't be involved in resonance going away from the ring. So there's no resonance happening away from the ring, they're just getting dumped into the ring. And notice that if you were to think of this in terms of resonance, this lone pair here is allelic to the pi bond here. It's one atom away from an atom in a double bond. And so you can draw a resonance structure where that goes to create a pi bond, and this pi bond creates a lone pair. But now this lone pair is allelic, so that can go to create a pi bond, and this can create a lone pair. But now this is allelic to this, so that can go to create a pi bond, and this goes to create a lone pair. But now this is allelic to, but now this lone pair is allelic to this other pi bond, so that can go to create a pi bond, and you end up with your original structure. So you'll notice that these are all resonance structures. The true structure never looks like any of these. The true structure is only ever the average of all of them. And you'll notice that when you average these, you have this negative charge with extra electrons on these carbons in the ring. And so the fact that you have those extra electrons in there means that that ring is going to react faster and it'll be more activated. So those are strong activators. You recognize strong activators because they'll have a lone pair on the benzylic position, and that lone pair, or if you have more than one, those lone pairs won't be involved in resonance going away from the ring. Okay, so far if we're summarizing our information, so far we know strong activators, lone pair on benzoic position, no resonance away from the ring. Okay, well what if you do have resonance away from the ring? First of all, what would that even look like? For example, you'd have those lone pairs again, and they're still allylic to the ring, so you'd still get them spreading out and pushing themselves into the ring. But notice here, the lone pairs are also allylic to a pi bond away from the ring. And so these lone pairs go toward the pi bond, and the pi bond forms a new lone pair. You get another resonance structure. So this resonance going away from the ring pulls the lone pairs away from the ring, and they don't dump themselves as much into the ring. Now they still do dump themselves into the ring. You still get all those resonance structures where this allylic lone pair goes toward the ring, and you get all of those resonance structures with a negative charge in the ring. So you're still activating the ring, but you're not activating it quite as much, because in addition to the the benzylic lone pairs going into the ring, they're also going away from the ring because of this resonance that's going away from the ring. So that's how you can recognize a moderate activator. You'll have a lone pair on the benzylic position, but there will also be resonance going away from the ring. Okay, you could have one other type of activator. These are weak activators. Weak activators are any alkyl group. Remember, alkyl groups are just hydrocarbon chains. So if the carbon connected on the benzylic position is just a hydrocarbon, just hydrogen carbon there, doesn't matter what the group is, that is an alkyl group, and that will weakly activate the ring. Now it's weakly activating it because of something called hyperconjugation. Let's sort of zoom in on the orbitals on these two atoms here. The benzene ring is going to have a p orbital, right? That's how it has these pi bonds. And this carbon here is sp3 hybridized, so it will only have sp3 orbitals. And that's true in each of these cases. So here we have the carbon in the benzene ring with its p orbital. And right next door we have the sp3 hybridized carbon, in this case in the methyl group. Now, this is tetrahedral, so these two sp3 orbitals are coming out. This one's coming out at us, this one's going away from us. Those don't line up with the p orbital at all. But this one sp3 orbital on top does kind of line up with 1/2 of the p orbital. The alignment is not very good. It's not very strong, and it's only with 1/2 of the p orbital. It's not with the whole thing, but it's enough. It's enough for these electrons to leak in the alkyl group, the electrons on this sp3 hybridized carbon, to leak a little bit into the p orbital. And when one of the sp3 orbitals on an sp3 hybridized carbon leaks into a neighboring p orbital, that's called hyperconjugation. So this allows these sp3 hybridized carbons to donate some electron density into the ring, to push some electrons into the ring. And so that's why they are activating. It's not a strong interaction, so they're weakly activating, but they're still activating. So far, this is the point that we're at. Strong activators, lone pair on the benzylic position, but no resonance going away from the ring. Moderate activators, you still have the lone pair on the benzylic position, but it's being pulled away by resonance, away from the ring. Weak activators are alkyl groups. So now we're getting into, let's talk about the types of branches that can pull, instead of pushing electrons into the ring, they pull electrons out of the ring. And that makes the ring have less electrons and so be a worse nucleophile. So they deactivate the ring. The weakest of these are the halogens. So remember, that's everything in group 7A. So you have fluorine, chlorine, bromine, and iodine. And they're really electronegative. So they use their electronegativity to pull the electrons out of the ring. And that's what makes them deactivating. Their electronegativity pulling over several bonds. That's what induction is. Electronegativity pulling over several bonds steals some of the electron density out of these rings. So the halogens are weak deactivators. Now, if you want to deactivate the ring even more, a stronger effect than induction is resonance. You might remember when you were talking about acidities in Organic Chemistry 1, you had the acronym ARIO. You look at the atom, and then you look at resonance, and then induction. Remember, in that series, the R comes before the I. Resonance is more important than induction. It has a stronger effect than induction. So when would you have resonance? Well, you'd have resonance if you have a pi bond on the benzylic position to an electronegative atom. Another way of saying that is to have a pi bond to an electronegative atom conjugated with the ring. Remember, conjugation is when you have alternating single and double bonds. So double, single, double. So if you have a pi bond on the benzylic position to an electronegative atom, that's going to be a moderate deactivator. And the reason is, one of the resonance structures here, so notice, pi bond on the benzylic position to an electronegative atom. One of the 5 resonance structures you learned in Organic Chemistry 1 was when you had a pi bond between atoms of differing electronegativity. And when you had that, you get another resonance structure where the electrons in that pi bond just go straight onto the more electronegative atoms. So notice this oxygen has 2 lone pairs. The electrons in this pi bond go onto the oxygen, so now it has 3 lone pairs. But that creates formal charges. So this oxygen now has a full negative charge, and the carbon is missing those electrons. It has a full positive charge. That carbon now is allylic. It's one atom away from the atom in this pi bond. That's another resonance form. When you have an allylic positive charge, the pi bond, the pi electrons go toward the positive charge. Because you have, this is an empty p orbital, and you have 2 p orbitals here, so really this charge spreads out. And that's what this is trying to communicate. So those electrons go there, you get this new pi bond, but now you have this positive charge, which is allylic here. So that goes toward that. Now you have this positive charge, which is allylic here, so that goes towards that. And so you can see how when you draw these resonance structures, you can see very clearly how you get these positive charges in the ring. That's telling you that there is less electron density in the ring. And so this ring is not going to act as good of a nucleophile. So you're deactivating the ring, and you're doing it with a moderate deactivator. So these are moderate deactivators. You'll recognize those by pi bonds to an electronegative atom on the benzylic position. The position that's conjugate, that would give you a pi bond conjugated with the ring. Lastly, you have the strong deactivators, and there are just 3 specific molecules here. You have the nitro group. This is 3 very electronegative atoms, and if you drew this out, you'd see that there's also resonance that's pulling the electrons out of the ring here. So that's the first thing. You would have an ammonium group. That's a nitrogen bonded to 4 atoms. So you have a really electronegative atom with a full positive charge, which makes it attract electrons even more. So that really pulls the electrons out of the ring. Or if you have the benzylic position with 3 halogens, the electronegativity, the induction of all of those 3 halogens act together to really pull electrons out of the ring. So in these 3 cases, you'll have a strong deactivator. Now notice the R groups here, those are any carbon chain. And so those can be any carbon chain, it doesn't matter. The important thing is that you have this ammonium on the benzylic position. And then these X's are any halogens, so fluorine, chlorine, bromine, iodine, it doesn't matter which one. So those are our 3 strong deactivators. So we've sort of built up this table. We're going to use this table in future problems. And this is how we can think of any branch on a benzene ring as activating the ring, making it react faster, or deactivating the ring, making it react slower. Now it turns out that these activators and deactivators have one more influence on the second branch you're trying to add to the ring. And that is that they influence where the branch attaches. They direct the branch to attach to specific places. So these activating and deactivating groups have a second effect on the product you get. They have these directing effects. Your new branch is going to be directed to a certain position by the branches that are already on the ring. The first rule, the big rule, is that all activators push the second branch onto the ortho and the para positions. So you could say all activators are ortho-para directors. Now, if you think about the reason why has to do with the stability of the sigma complex. So if you notice what we have here, we have a strong activator. This oxygen has a lone pair. That lone pair is on the benzylic position, and it's not being pulled away through resonance away from the ring. So this is a strong activator. And they're giving us a nitronium ion. You'll recognize that from the nitration of benzene, but this could be any electrophile. Let's think about what happens if we have this strong activator on the ring, one with lone pairs on the benzylic position, and we react it with an electrophile, and what happens if the electrophile attaches to the ortho position versus the meta position? That's 1, 3, versus the para position, that's 1, 4. Remember, ortho is 1, 2, meta is 1, 3, para is 1, 4. Well, in that case, you would form sigma complexes. But with the ortho attack, you would see that you would get an extra sigma complex. You get you get an extra resonance structure. There are 4 different structures in the sigma complex. With meta attack, you would get 3 resonance structures. And with para attack, you would get 4 resonance structures. I encourage you to pause the video and see if you can follow the movement of all these electrons with these resonance structures so that they make sense. They're all working by moving around in a allylic positive charge. The pi bond always goes toward the positive charge to give you your new resonance structure. Okay, so let's think about what this means. Resonance tells you how much electrons are spreading out, how much charge is spreading out. The more resonance structures you have, the more charge is spreading out. And the more charge spreads out, the more stable the molecule is. So because the ortho attack and the para attack gives you more resonance structures, that sigma complex will be more stable, and that will be your product. It's these that you're going to attach to. If you form this, it'll come undone, and quickly it'll get snapped up by an ortho-para attack. So because the ortho and para attack gives you a sigma complex with more resonance structures, the sigma complex is more stable, and these reactions happen faster, and they're the product you end up getting. You get ortho and para products. Now, if instead of having a lone pair on the benzylic position, you have an alkyl group, so like in the case of weak activators, you still get a preference for the ortho and para position. But it's not because of the number of resonance structures. So if you imagine you have this alkyl group and you're adding some electrophile, they're just using nitronium, but they could use any electrophile. What would happen if it attacked the ortho, meta, and para positions? Well, if you draw out all the resonance structures, you'd see that each of these sigma complexes has only 3. But the ortho and para attack is still preferred, and the reason why is because with ortho and para attack, you have a resonance structure where there's a positive charge right next to the electron donating group. Remember, the sp3 orbital on this is pushing electrons into this ring through hyperconjugation. So this is a wonderful place for the positive charge to be. It's as if it's a hot day and a fan of electrons is flowing onto it from this alkyl group. So this is a great place to have a positive charge. This is a very stable resonance structure. Now you don't get a resonance structure with the positive charge next to the electron donating group in the meta attack. But you do get a resonance structure with the positive charge right next to the electron donating group with para attack. And so it's because you get this really stable resonance structure in your sigma complexes that ortho-para attack is preferred for these weakly activating alkyl groups. So the big takeaway we had there is that all activators are ortho-para directors. If you have an activator on the ring, the second thing you add to the ring is going to go at the ortho position and at the para position, not at the meta position. Okay, let's think about deactivators. And we want to think about these in sort of 2 different groups. First, you have the halogens. The halogens are deactivators, but they're ortho-para directing. And that's because they also, like most activating groups, they have that benzylic lone pair. They have that lone pair on the benzylic position. And so when you have these different attacks, ortho attack, meta attack, para attack, you get these sigma complexes in these boxes. And just like with the strongly activating groups, the sigma complex for ortho attack has 4 resonance structures. Sigma complex for para attack has 4 resonance structures. The sigma complex for meta attack only has 3. The extra resonance structure in the ortho and para attack is telling you that that sigma complex is more stable. The charge is more spread out there. And so that's how the reaction proceeds, through that more stable intermediate. So if you have a halogen on your molecule, that halogen is going to direct the second thing you add to the ring to the ortho positions and to the para positions, because that gives you the more stable intermediate. So far we can sort of summarize what we've talked about with these directing effects. All of the activators and the halogens are ortho-para directors. All of the other deactivators, the moderate deactivators and the strong deactivators, are meta-directors. So if we go through the same thing here, and here we have a strong deactivator, the nitro group, what happens if we add an electrophile on the ortho position, the meta position, and the para position? Well, for the rest of these deactivators, you'd only get 3 resonance structures in your sigma complex, but a similar thing happens here as happened with the alkyl groups. you end up with a positive charge. With ortho and para attack, you end up with a positive charge next to your branch. For alkyl groups, that was great, because alkyl groups were pushing electrons into the ring, so that helped to stabilize this. But for the moderate and strong deactivators, they're pulling electrons out of the ring. So this is really an unstable place to have a positive charge. Positive charge right next to a place that is sucking electrons out of the ring. It's very unstable. And so this resonance structure is a very unstable resonance structure. Likewise with para attack, you get one that has the positive charge right next to the electron withdrawing group. The electron withdrawing group is pulling electrons to itself. Having a positive charge there is very unlikely. So these are very unstable resonance structures, and so they're disfavored. The meta attack doesn't have a positive charge next to the electron withdrawing group, and so it's relatively stable. And so so this is more stable than this sigma complex is more stable than the ortho-para sigma complex, and so the meta attack is preferred. So to summarize the entire discussion, we have activators and deactivators. They're all classified as strong, moderate, and weak, according to the rules that we learned. All activators and the halogens are ortho-para directors. The moderate and strong deactivators are meta-directors. So this is the reasoning behind this table. We're going to use this table a lot when we think about synthesizing polysubstituted benzenes, when we think about putting more than one branch onto benzene rings. And so we gave this sort of reasoning, this explanation behind all this table that we're just going to use in future exercises.